All right, today we're diving into one of the biggest, most ambitious challenges in all of science. It's a question that smashes together biology, computer science, and honestly, a little bit of philosophy.
It seems like such a simple question, doesn't it? But the answer is, well, it's unbelievably complex. To even think about simulating a brain, you first need a perfect blueprint. And then you've got to have a way to test if your simulation actually, you know, acts like the real thing. So let's see how scientists are tackling both of these massive problems. So here's the game plan. First, we'll dig into the incredible, painstaking effort to map the brain's wiring. Then we'll see if we can use those maps to actually predict what the brain does. We'll check the report card. How well are we doing right now? And finally, we'll look ahead. What's next on this absolutely monumental quest?
Okay, part one, the blueprint, or connectomics. Every big construction project, right? It needs a blueprint. For the brain, that special blueprint is called a connectome. It's the full map of all its crazy, intricate wiring.
Think of a connectome as the ultimate circuit diagram. It's a map that doesn't just show you every single neuron, but, and this is the important part, every single connection, every synapse between them. This is the physical hardware that makes all our thoughts and actions possible. And making one of these maps, wow, it is a truly mind-boggling task. First, they take brain tissue and slice it into thousands of layers, each one thinner than a human hair. They image every single slice with an electron microscope. Then, powerful computers stitch all those flat images back together into a 3D model. And after all that, human proofreaders have to spend literally tens of thousands of hours just correcting the mistakes the computers made. It's a huge effort. All of that incredible work led to a massive breakthrough you see here, the HemiBrain project. This is a nearly complete wiring diagram for a big chunk of a fruit fly's brain. It's a huge landmark, our first really detailed blueprint of a brain this complex.
And the scale is just staggering. We're talking about almost 25,000 neurons and 20 million connections between them, all mapped out. This gives us a look we've never had before into the circuits that control everything a fly does, from flying to finding food.
But let's be real, a fruit fly brain, as cool as it is, isn't a human brain. So what happens when you try to use these same techniques on a piece of our own noggin?
Well, this is what happens. This is the H01 dataset. It is a map of just 1 cubic millimeter of the human brain. That's a tiny sample, smaller than the head of a pin, that was taken from the cortex of a patient during a surgery.
And here is where things get absolutely wild. This tiny, tiny piece of human tissue has an estimated 150 million synapses. That is more than 7 times the number of connections in the entire fruit fly hemibrain we just saw. The data for just this 1 cubic millimeter takes up 1.4 petabytes. That's like a million gigabytes. It's just an insane amount of information.
So we're getting these blueprints, these amazingly detailed static maps. But a map of all the streets in a city doesn't tell you anything about the flow of traffic, right? To get how the brain works, you have to see it in motion.